Hey everybody, so I just wanted to make a quick video on like a question like 24 on the homework. So we have this matrix A which equals like 1, 1, 0, k. And you're basically asked to find all the like real values for k which would make it diagonalizable. And it's kind of tricky, and I think it's good to, I probably should have put one in the lesson in the video somewhere, because I actually ended up giving you a few of these. But, and someone asked about this, and I think it's definitely a good one to go over. So you kind of start off and you can like sort of assume you're going to be able to, so you're going to need like eigenvalues and all that, right? So we're going to take the determinant of a minus lambda I. And in this one, that would look like 1 minus lambda, 1, 0, k minus lambda. And we're setting that equal to 0. So we got what, 1 minus lambda times k minus lambda. And that needs to be set equal to 0. And so it's looking like if lambda was 1 or lambda was k, then you would get eigenvalues, right? And I mean, that makes sense because this is an upper triangular matrix, and so the eigenvalue should be right there on the diagonal. And so then what you can kind of do is you can just go and like, you're going to take each one of these, and since you have, so you could have repeated roots, I guess, if k was 1, but most of the time, right, you're going to have like distinct roots here. And what I'm basically thinking of is that condition with the geometric multiplicities needing to match up with the algebraic multiplicities, right? So I basically want to think about the possible eigenvectors I can get out of like each value here, and think about if it would be possible to get enough or to even get, I guess in this case, eigenvectors out of them. So if I do this one, A minus lambda I would become the matrix 1, 0, k minus 1, okay? And we really just want to RREF this thing, all right? So if I was going to RF this thing, this is kind of that annoying stuff. We ran into this earlier. Basically, I would divide. I would kind of have to do this one out by hand. So I'm going to divide by k minus 1. And this is basically where there's going to become an issue. And so let's see. So if I divide by k minus 1, I'm doing that to make that a 1, right? Actually, sorry, never mind. I'm going to do this a better way. I'm going to multiply the first row by k minus 1. So I'm going to get 0, k minus 1, 0, k minus 1. And then I'm going to just subtract the bottom row from the top one. And so I get 0, k minus 1, 0, 0. And then now this is where I want to, so I want to like REF this thing, right? So I'm going to divide by k minus 1 on top. So I get 0 and then 1, okay? But in order to do that, I had to do row 1, divided by k minus 1. And this is going to be kind of the issue. So now if you look at it, it's basically saying that, I really actually augment this thing with 0 the whole time, so it doesn't really change much, just 0, 0, augment, 0, 0, augment, 0, 0. And so it's saying x2 is 0, and then x1 is free. So basically any vector of the form like t0 is eigenvector here. All that work just to get to that. So anything like that would be an eigenvector for 1. But along the way, I had to assume I had to be able to divide by k minus 1 kind of to see that, okay? And you don't really even have to, I guess, divide by k minus 1. You could just say that like k minus 1 times x2 is equal to 0, right? So k could be 1, or x2 is 0, but either way it's going to take you back to like a vector like this. So for the other one, so for like lambda equal to k, right, you're going to do a similar thing. You're going to RAF this matrix, 1 minus k, and then 1, and then really let's put the 0 in this time, and then 0, and then k minus k, which I guess I'll just put it for right now. And so I would get 1 minus k, 1, 0, 0, 0, 0. Okay? And what we get out of this thing then is 1 minus k x1 needs to equal negative x2, or x1 needs to equal negative x2 over 1 minus k. All right? So if you just let like x 2 be t, or 1, sorry, let's do 1. So let's just let x2 be 1. Then you get a vector of the form negative 1 over 1 minus k, and then 1, right? So basically any scalar on that is going to be an eigenvector. And so the whole long story short here is I can get a linear, like a one-dimensional eigenspace for this one eigenvalue given that structure, and I can get a one-dimensional eigenspace for that one eigenvalue given this structure, right? And along the way, the only issues I ran into was I had to divide by this 1 minus k and stuff in here. And so if you ever like run into that one of these problems, you see that this would work 100% of the time so long as k doesn't equal 1. So everything else here works. So all the real numbers for k work, but 1. Okay, that's basically the answer for what k can be. K can be any real number there but 1. They're kind of weird problems. It's mostly like I'm sort of doing like educated guess and check, but like the idea is I'm going back and comparing it to that theorem where it relates the geometric and algebraic multiplicity. So hopefully this video helped.